This lecture is a follow-up lecture to the statistical decision theory, and this is statistical inference of mean. And we will talk about here a T distribution and different types of problems in which we use estimates from one sample or when we try to compare two different samples. Similarly, in statistical decision theory, there is another topic which is the statistical inference of variances. In this lecture, we will discuss the examples in which we say the variances are known to be compatible or they are known to be different. So let's see what how do we proceed. Okay. So the applications are one sample problems and two sample problems. And in two sample problems, we will talk about one example for unpaired t-test and one example for paired t-test. So the t-test appeared in 1908 and with the cover name uh, suggested by the person William Gossett for himself was a student. Therefore, the famous name is student t-test. So the person William Gossett found a way to compare small samples where the sample size is less than 20. So this work was so novel that to some statisticians, Mr. Student was the Faraday of modern statistical methods. So the distribution he came up with is a distribution in which the population variance is unknown and therefore it is estimated from sample as S squared. So we will talk about the inferences of means where the population variance is unknown. Therefore, if we see the expression of the t calculation, it is like the z-score calculation. So you can notice here is x bar minus mu. The numerator is same as it was in z-score, but over here the sigma, the population variance has been uh, uh, population standard deviation has been replaced by s, which is estimated from the sample. And now there is the square root of n. The sample size is going to show up over here. It means as the sample size is going to change, so the distribution is going to change. Therefore, the symmetric distribution, like normal distribution, the t distribution additionally depends on a parameter n minus 1, which is known as the degrees of freedom. And this is to emphasize that one parameter has been estimated from the sample itself. So in this statistical inference, we are using the inferences of mean. However, in this process, instead of population variance, we are going to use the sample variance. Therefore, the degrees of freedom are n minus 1. So here are the representative pictures, the graphs of t distribution. It is symmetric like the normal distribution, however, with heavier tails. So like you can notice, the degrees of freedoms are 3. Therefore, we have the a bit lower peak, however, the grave tails. And as the degrees of freedoms are going to increase, the peak become higher and the tails become lighter and lighter, and it approaches to normal distribution. And it is said that as the sample size increases above 20, so we can assume the sample variance is equal to the population variance, and the calculations can be done with the normal distribution table. This is the t distribution table. This table is given in a slightly different way. So, for example, if we read the leftmost column, here df is written, which is degrees of freedom. So we have its definition. It is n minus 1. And at the top we can read, it is written one tail probability. So one tail probability, this is going to be the level of significance. So at some given level of significance, the abscissa values are given. And the significance level has been defined only in the upper tail. So since the distribution is symmetric, so the one tail probabilities in the left tail or the lower tail, they can be estimated from the same one, and also the abscissa values are going to be the negative of the value given over here. So these are the one tail probabilities. Like if I consider a value of T5, so at 5 degrees of freedom and at 1% level of significance in the upper tail. So what's going to be abscissa? Let's consider I have to look for the value in the at 5 degrees of freedom and 1% probability. So 1%, so 3.365. Let's see. Okay, in the row with 5 degrees of freedom and in the column with 1% uh, 1% level of significance. So here is the value 3.365. This is the abscissa value. So if someone is looking for the value in the lower tail, the abscissa value for lower tail at 1%, that is going to be minus 3.365. So student t-test, population variance is unknown, and we are going to use the S squared, the samples variance, in place of population variance. So hypothesis testing, the hypothesis is about the mean value of the population from the mean value estimated from sample. So the null hypothesis is that the mu1 is as good as mu, and the alternate hypothesis is that mu1 is different from the old mu value, that the present measurements suggest uh, a change in the mean value which cannot be explained by the indeterminate sources of errors. So there is some special source of error uh, which is dragging the value of mu. So it means we have to investigate further. So the confidence intervals can be estimated by the t critical values. So the lower limit is the mean value from the sample minus the t critical value at some level of at some degrees of freedom and level of significance times s over square root of n. So s has taken the place of sigma and t has taken the place of z if we compare these expressions to the earlier learned normal distribution and confidence interval expressions. So here is the first example. So adopted from Professor David Harvey's lecture notes. So the statement says, before determining the amount of sodium carbonate in a sample, you decide to check your procedure by analyzing a standard sample that is 98.76% weight by weight sodium carbonate. 5 replicate determinations of percent weight by weight sodium carbonate in the standard gave the following results. So we have 5 numerical values using alpha equal 0.05. Is there any evidence that the analysis is giving inaccurate result, which means there is more variation at the level of 5% at significance level. So we will have the sample size. We have the sample mean value and the S computed from the same sample, and alpha is 5%. So we will calculate the t-score or t-calculated value. It's 3.91. Since we are looking for the variation inaccuracy, as the word suggested in the statement, so we would like to read the value for t when it is 3.91. However, there is one thing to be noticed. It is 5%. So we have to consider this alpha to be divided into two parts. So let's read a value at the 4 degrees of freedom and alpha by 2, which is 2.5%. So here, okay. So 2.5% and 4 degrees of freedom. So it's a value 2.776. So 2.776, it is going to be a value, positive value, which defines the upper limit for t value, and minus 2.776, it marks the lower value, which are required to calculate the upper and lower limits of the confidence interval in X variable. However, if we see the calculated value, so calculated value 3.91. So this is the observation which is beyond the confidence interval. Therefore, there is another way to write the results of hypothesis, that the ideal value or the calculated value, the ideal value from table, which marks the limit of confidence interval, is less than the calculated value. So therefore, the calculated value or the observed value, it falls outside. Therefore, there is some determinate source of error. So the concentrations are not consistent with the standard sample. So there is a need to check the procedure. So the inference is we reject the null hypothesis and accept the alternate hypothesis. So we report the results that at the 95% confidence level, the difference between X bar and mu is too large to be explained by the indeterminate sources of error or random errors, which suggests there is a determinate source of error that affects the analysis. Professor David Harvey. So thanks to Professor David Harvey. Okay, there is the example from our reference book. A certain dimension is measured on 4 successive items coming off a production line. This sample gives X bar mean value 2.384 and a standard deviation for sample is 0.048. On the basis of this sample, what is the 95% confidence interval for the population mean? So it's a straightforward problem. I hope students can carry out these calculations. Here is a bit of reference. N equal to 4, X bar, S and alpha 5%. So the interval requires lower and upper limit to be estimated. Here, the degrees of freedom are going to be 3, and alpha by 2 is again 2.5%. So this is going to be the T critical value, and then uh, one can proceed for calculating the lower limit for the mean and the upper limit for the population mean. So it's just a matter of doing the calculation. Here are the marks for the lower and upper limits in T distribution. So the other modality of T distribution is to compare two sample problems. So while comparing the two samples, our procedure will be like defining a new variable at the first step. So which is to define a difference between sample 1 measurements and sample 2 measurements. Then we will calculate the test statistic for the new variable d. So d minus mu d over st, which is the standard deviation, and we will be uh, calculating the inferences about this difference variable. So if the both samples belong to the same population, which means from sample to sample there is no variation, uh, like the measurements taken regularly after some interval, like the interval of 5 hours or a day. So the measurements taken at regular intervals, they do not differ from each other. So we require such comparisons, and the inferences are to be made for the difference variable. So after the difference variable calculated, we will calculate test statistic, and then we will compare against the tabulated values. So first modality is unpaired t-test. So the assumptions are the samples are from same population and their variances are compatible. We will take this one for granted while solving the problem from these exercises. However, uh, there is a complete test which suggests how to calculate the variances, the compatibility of variances, how to make inferences for the compatibility of variances. Well, the unpaired t-test is applied while comparing the routine set of measurements, like the measurements taken after regular intervals, or it is to compare the measurements from similar instruments. So the similar instruments are kind of calibrated with the by the application of unpaired t-test. If the differences in the similar instruments are not very large, then um, then we can infer that the instruments are working properly. Okay, so we will define with the difference variable from sample 1 and sample 2. Well, in unpaired t-test, both the samples can be of same size, which means n1 may be equal to n1 or it may be different. Okay. So after that, we would like to calculate the standard deviation in this variable d. So for calculating the standard deviation in d, which is required in t test statistic calculation, so we will first calculate the pooled or combined variance. So we assume that the two samples belong to the same population. Therefore, if we calculate the average value that is going to be a good representative of of their population variance. Oh, pardon for the square missing over here. Well, I can put that one right now. Right now, how I can put that one. So, okay, pick up a pen here, and then, so here it is too. Okay, right, I'm trying hard to put here a 2. Okay, so it is square. So it is a weighted average value of the variance from sample 1 and sample 2. So the weight is n1 minus 1 and n2 minus 1, because n1 and n2 are the sample sizes for S1 and S2. And then this variance representative of population will be used to calculate variance in the D variable. So calculate the variance in variable D. So when two quantities are added or subtracted, so we know how to calculate the variance in the resultant quantity. So this is going to be the situation. So SC squared times 1 over n1 plus 1 over n2, it is the variance in the difference variable. And then we will go for the calculation of test statistic, which is the d minus mu d over st. When the two samples are from the same population, therefore there is going to be negligible difference between their mean value. So this mu d must be equal to 0. So then we will make the inferences. Okay. So and then if we would like to define the hypothesis, so mu d is equal to mu1, so which is which should be 0, and alternate hypothesis is that the both samples generate a measurable, a significant difference from 0. And likewise, the confidence intervals are to be calculated accordingly. Okay. So here is the example. Two methods of determining the nickel content of steel are compared using 4 determinations by each method. The results give the mean values from samples and standard deviations from the samples. And we have 3 degrees of freedom. Assuming that the two estimates of variance are compatible, so without applying the F or chi-square test, we are using this statement. So we have to consider that the difference in means statistically significant at 5% level of significance. So we have to consider the statistical significance. So n1 x1 bar s1, n2 x2 bar and s2. So we have the apparent difference in x1 and x2, and we have to consider at 5% level of significance that there is whether statistically significant difference or not. So we will go through all these calculations by defining the difference variable. We will calculate the pooled or combined variance value. Then we will calculate the variance of the difference variable, and we get to the t calculated value. It is 4.38. It is the calculated value. from the table, we have to we have to pick up the ideal value, and our hypothesis is mu d is equal to 0 when both samples represent the same population. So ideally, there must be no difference suggested from those measurements. Otherwise, the difference must be a significant one. So here is the situation. The degrees of freedom will be calculated as n1 plus n2 minus 2. It is 6. And at the 6th level, at 6 degrees of freedom and 5% level of significance considered on both sides, we can see here that the observed value, which is okay, 4.38 value, it falls much beyond the confidence interval limit, which is at 2.447 and minus 2.447. So the value falls in the rejection region. Therefore, null hypothesis is rejected and inferred as that there is a significant difference at the 5% level of significance. The other modality is the paired t-test. So the paired t-test is identified with the characteristics of measurements when the experiments contained paired measurements. So it means the two sample measurements are taken together. So the applications are comparison of different instruments. It means all the sample objects, they have been tested by the different instruments. So at one time we have the measurement from two different instruments. And similarly, this is also applied to the comparison of measurement techniques. So in this case, we can define the difference variable on the basis of individual values from two different samples, because every time we have one measurement for x1 set and one measurement for x2 set. So we can define the difference variable. We can calculate the standard deviation or variance. Variance is the fundamental quantity, variance and then standard deviation for the difference variable. And then we will apply the inference for the difference variable. So if the two instruments are giving the similar results, then mu d must be equal to 0. So this is straightforward and easier than the unpaired t-test. Okay, so these are the steps. And let's see the example. So we decide to run a test using an experimental evaporation pan and a standard evaporation pan over 10 successive days. So two different instruments are going to be compared. Okay. The two types are set up side by side so that the atmospheric conditions should be the same. A coin is tossed to decide which evaporation pan is on the left-hand side and which on the right-hand side on any day. The measured daily evaporations are as follows. So we have the data set. So pan A values for successive 10 days. These values are given over here. And the evaporation pan B, the values are given. So we can define the difference variable on the basis of the differences in the individual set values, right, from pan A and pan B. So right now it is A minus B. Okay, so some values, well, majority of values are higher and one value is smaller. So we would like to see this question. Does the experimental pan A give significantly higher evaporation than the standard pan B at 1% level of significance? So here one thing needs to be noted, that the way the difference was defined. So here we are going to test that pan A give significantly higher evaporation. So when we have decided to look for higher values or lower values, then one tail test must be applied, and we can consider we must consider the significance level in one tail. So we will go through the calculations. First, we define the hypothesis that mu d, that there is no difference between the measurements from pan A and pan B, and mu d is greater than 0 to highlight the significant difference. This is going to be the statement of alternate hypothesis. So we will go through the calculation. D bar is 1.62. SD bar is 1.548. And if we go for the T calculation is 3.31. This one is about the mu D value 0. So this is the calculated value. And if we look for the ideal value, so for 9 degrees of freedom at 1% level of significance, the ideal value is 2.821. So the significance level has been identified in the upper tail, and the observed value falls in the significance level. So over here, the difference is significant. So the calculated value is greater than the ideal value. So the value falls in the rejection region. Therefore, null hypothesis should be rejected and inferred as the experimental pan A does give significantly higher values in this setting. So this takes us to the end um, of the inferences for mean. Well, there are the softwares provide more options than the one discussed in this lecture. So there are other modalities of uh, unpaired t-test. Well, pardon for the title shown here. Okay, let me correct that one instantly. Okay, this example is about the paired t-test. This is paired one, and okay. So, well, this remained, this was a typo, remained over there. So this is the utilization of T distribution and the applications in the context of unpaired and paired t-test. Well, there are other modalities of unpaired t-test in which there is one in which we consider that the samples are from different population. So, however, the complete procedure will remain the same in this context, that we will define the difference variable. Then we will go for the test statistic calculation. Then we have to have the inference, and over here the calculation of degrees of freedom would be different. There is going to be sometimes a weird or a special equation that show up while going through those problems. So with this, I really hope that the students can go through the problems and examples given and discussed in the reference books, or from any other a reference book, they can also pick up the problems of their own choice.